This is Dr. Tesler for Operating Systems in the fall of 2020 at Towson University, and today we will be discussing Chapter 3, Processes. This will be one lecture to cover both days of the week, so you may wish to pause in the middle where there is a scheduled break where you'll have a question that you might want to address. So make sure that you take your time and you've done the reading, and if you've done the reading, this lecture should just assist in that comprehension. You should be okay. So let's get started. In our last week of class that we had lecture, we went over operating systems with the services they provide to users, how the operating system is structured, whether that's micro or macro kernel, and then the boot process, going from what the book refers to as a bootloader exclusively being the piece that comes out of firmware, then moving on to the boot program, which as its final purpose is to take the kernel, load it into memory, and begin execution at the first instruction of the kernel. So from those services, those are the things that you want to make sure you can recall some of them, if not all of them, from the operating system to users to processes, such as creating and destroying processes, managing memory, and interacting with hardware on behalf of the user. So in Chapter 3, we'll discuss what a process is as a concept, how to schedule a process, operations on those processes, how processes communicate with each other, called inter-process communication, some examples of IPC mechanisms, and then the client-server model. So again, our objectives here are to introduce a process and talk about scheduling those processes, what IPC is, and then describe communication. So the concept of a process, I'm sorry, I had those backwards. There will be some terminology that's used interchangeably. I prefer the term job to process. That's where I come from, but we can use them. They are synonymous in the book and in the lectures here. That we have a process that needs to run and to do something. Whether or not that's actually in memory, that's what the book is trying to draw the distinction from. So in a batch system, you'll have a job, and that is a program that's being asked by the user or by the system to be executed, but it's not yet in memory and stored. So that batch system, remember, we would submit a large collection of jobs to run one by one, and those jobs correspond to a program. So the job is not really passive because it's in queue waiting to do something, like the program is passive just sitting on disk. So moving it from being just a program on disk into that queue to be executed, that's where they're trying to draw that distinction. From a conceptual standpoint, it's a subtler distinction and not really a huge difference. I might even still call that a process, one that's just not in memory and loaded, that it might be a swapped out process, which we'll get into a little bit later in the lecture as well. So that's the batch system, where we submit a bunch of jobs. They are waited to be, the operating system will choose one by one to execute them. In a time-shared system, there might be multiple processes that are waiting to get access to the CPU so they can interact, so they can execute in a way that seems like interaction is immediate. So again, I will use the term job. That's just where I come from. It's the same as process. In the batch system, there's that difference between whether or not that job is yet in memory and executing, or if it's waiting to turn into something that's on memory and running on the processor. So a process is a program in execution. And we say that a process executes in a sequential fashion here. What that means is that it has a start and an end. There may be multiple loops, there might be control flow, but the idea is that the process will at some point terminate. And I'll take myself out of here. A process has multiple components that live in memory. So what you're seeing on the right-hand side of the slide here is the view of memory of a process in memory. And the code of the program may be loaded. This is just an example of how these might be ordered. that the text section, that's the actual source code, that's the program that's running. And the data section, that's the global variables available to the entire process. Then there's the heap, that's memory that's allocated dynamically if you've created a new object or malloc some memory. And then there's the stack, and the stack is a LIFO, last in, first out. So you push something onto the stack, you pop it off the stack, and this is where your local variables for your functions will go. So if you declare a function with 4 integer variables, then 4 integer variables will be pushed onto the stack. So that's the way that we will view a process in memory. This is one way that it might be laid out. The order doesn't matter, but the concepts are there, that their stack, that will grow, heap will grow, and sometimes they will grow into each other. That's where you might have heard the term smashing the stack. And there's an excellent document out there if you're interested in that kind of attack called Smashing the Stack for Fun and Profit. So again, the book really does stick with this idea of calling a program passive. It's a good analogy that a program is passive and a process is active, that the executable sits on disk waiting to become active. It's passively doing that, just sitting there doing nothing. And then when it is loaded into memory, it becomes active, waiting to execute. And the important concept here is that one passive entity, one program, can be several processes. So that multiple users may execute the same program, like a web browser on the same computer, or one user may execute multiple copies of the same program. So as a process has a lifetime, and it goes from being a new process, being born, to dying as being terminated. So when you request a new process to be executed, then it is in the new state. And these states may all be enumerated on an operating system, or there may be this many states, or there may be more states available in your operating system. This is one model, but the idea is that a process has a state and it flows between those states, like your deterministic finite automata or your NFAs. The idea is that we start in an initial state, which in this case is new, it's just been created. The operating system needs to take some action to decide whether or not this process can be executed and to set up the necessary resources to run the process, and then the process becomes ready, meaning that it is ready to execute instructions. When the scheduler selects this process to run, then it moves it to the processor where it is running instructions on the CPU, and on the processor. And it's only possible for one process to be executing instructions on one CPU, one processor at a time. So we go from new to ready, saying I'm ready to run my code, then the process begins running its code, and if it has nothing else to do, then it exits, it terminates. A process may also be interrupted by the operating system, which it will go back to the ready state, or it might request information, say from a device, that would require an interrupt, or the networking some other piece. So when it issues that request, it moves from running into waiting for that input event or that output event to complete. When that occurs, the scheduler, the operating system, is notified, not the process, and it transitions the process back to the ready state, and later on it may select that process to run again, or it may wait until others are ready. To keep track of the state of a job, a process, there's what's called a process control block, also a task control block. That's the same. It's just a different name because this hasn't really been standardized across them. And what's different here from the diagram that we saw on slide 3.6 is this is a snapshot of a data structure. This data structure lives somewhere in the memory space of the operating system typically, or at least under the operating system's control. you wouldn't want the process to be able to manipulate this information. So that it has the process state, that is what we just went over on the previous slide, a process number, some kind of identifier for the process, and the program counter. Now the program counter is the address of the instruction that is going to execute next. And so that when the process goes from being running to waiting, that when it's resumed, there's a location within the source code that it can begin executing again. It also needs to store the registers, that is the state of the processor when it was interrupted running that process, so that when it is restored, that the task can begin running again with the correct information. Then there's potentially more information, such as how much memory the task is allocated, the files that are open, and maybe some more information about devices. This process control block will differ from operating system to operating system, but minimally, a program counter and the register are necessary for the operating system, if it is a preemptive operating system, to be able to make sure that that process is resumed. So what we have here is an example of two processes that are executing on one processor. We have process P0, and it's executing and it gets interrupted. And at that point, the running state, all the information on the previous slide, is snapshotted by the operating system and saved into the process control block. The reason for P0 being interrupted, we're not sure, it doesn't matter, but as it's interrupted and the operating system then selects the next ready process to run, it selects process P1 to run. And to get P1 to run, it takes the process control block of P1, loads the proper registers, sets the program counter, and begins execution. Then P1, after some time, issues a system call, at which point its process control block is saved to the operating system, and P0 is selected to run next, so the state for P0 is then loaded onto the processor before execution resumes. So make sure that you kind of get this basic idea that I have a process, it's running, okay, it's interrupted for some reason, or it's asking for information. We save that process control block state, all of it, before the scheduler will do, the operating system will do anything else to either handle that I/O operation, select another process to run, and then when a process is executing once again, it has to have its state loaded before it can do anything. So understand this diagram, at least in concept, the mechanism for saving information, not necessarily the detail we need to concern ourselves with just right now, but I have a process that's running, there's an interrupt, there's an I/O operation, so I save all of my state, and then before resuming that state, the operating system will restore it. We've been talking about processes as implicitly having a single thread of execution. And that thread of execution is sometimes the difficult concept. But for now, assume that when there is a process for this chapter, there's a process, there's only one program counter, one set of registers to execute. That is the key identifier of the thread, is the program counter. But that's not also known, it's a little bit shy of being true as well. But think that there is only one program counter per process control block. So if you were to add more threads of execution, then you would need multiple program counters as well as multiple register states. But this is not for this chapter. We'll explore this, I think it's in chapter 4. It might be later, but it's not in this chapter yet. So just for now, associate a thread of execution, and a thread of execution, though the definition is not given in the book, the intuitive way to think about it is a request to execute instructions. And I begin by making a request to execute a set of instructions from a program, and that has an entry point. So that one thread of execution says start executing at this instruction as this program executes, as it becomes a process and executes, it will tell you when it wants to quit. So a thread of execution is a request to start executing in some process, out of some address out of a program. So that's how you might start to think about it. For those of you that are interested in doing your projects on the scheduler within Linux, the description of a task struct, which describes a process, is a doubly linked list. And within that structure, there is a link to the parent process, the one that each process, the parent process, is the process that requested this process to execute. Then there will be a list of children, and those are the processes that this process requested be executed, along with a list of open files and the memory space of the process. That's the memory allocated to the process. And importantly, it must have a process ID and the state. And so this corresponds to that process control block that you saw several slides ago. Frames, thinking about cameras. So scheduling, or the scheduler, is one of the key operations of an operating system. And there may be multiple goals for a scheduler, and one of them might be to maximize the CPU, the other one might be to another objective might be to maximize responsiveness. The job of the scheduler is to select among the available ready processes that which to run. It also may decide to, it also may be responsible for admitting jobs or removing jobs from the list of ready processes. So the scheduler has a job queue, or that's all the jobs that are ready to run. Sorry, all the jobs that are not yet terminated. So they're somewhere between new and terminated. A ready queue, those are those that are ready to execute. And then this other idea of a device queue that is that we'll go through in the next slide, because I think it's a little easier to understand. So here what we have, to understand our diagram to start, the ready queue has a list of those process control blocks, and by being a member of this queue, that says that this process is in the state ready, that it is ready to execute. We notice that we have 4 device queues hanging over here, and the tape 0 is empty, but disk 0 is not empty. And what this means is that this process control block is this process that's associated with this process control block is waiting for the I/O operation to complete. So that's what it means to live on this queue. So that when the interrupt saying that the information is ready comes back to the operating system, it can go through this queue and figure out who was waiting for that data, or whose write has finished for that data. Similarly, for the terminal, there is task 5, job 5, that is interacting with the terminal. It's either reading or writing information from it, and when that operation completes, the process control block for this device will move from the terminal queue back to the ready queue when all that information is ready. So a process in the ready queue, indicated by a process control block, might move to the processor to execute, and then when it makes a request for information from or to the terminal, it will go into the queue for that terminal, and there it will be waiting until the operation completes. The operating system, after moving that process to that queue, will then select another process out of the ready queue to execute until the interrupt for that terminal returns telling us, hey, there's something, we're ready for this process. The process will be resumed by placing it in the ready queue and then later selected to run on the processor. Another way that we might view this transition is that task starts in the ready queue. and then moves to running by being placed on the processor until any of these operations take place. And an I/O request, where it then gets placed on the I/O queue, and then the I/O operation is serviced, where it moves back to the ready queue. On a operating system that works on time slices, if their time slice has expired, then the process will be pushed back to the ready queue. If the process forks a child and waits for that child to execute, then that might cause us to be placed in a waiting state until we can go back to the ready queue, or waiting for an interrupt causes us to be waiting, and then the interrupt occurs and we go back to the ready queue. So the concept of schedulers, we've talked about this a little bit, and earlier in some of the classes we may have described these somewhat inaccurately, but the short-term scheduler, this one we've been consistent with, is that if there is a job that is in either any of the states from new to terminated, that the scheduler will operate upon that job. So that means that the program that we turned into a process has been fully loaded into memory, and it's either ready to execute or it's waiting on an I/O operation. So it's in any of the three interior states, and so the scheduler can select from any of those processes to execute. The long-term scheduler is the one where we've been a little bit vague, and this is associated with batch processing. That we've placed on the list of jobs to complete this long scheduler that we know won't fit into memory, and the operating system will select from that list of long to run processes which are not in memory, those to load into memory, execute, and then select between the ones that are in memory and keep going. So that's the difference between the long and the short term. And a long-term scheduler will consume CPU cycles on behalf of the operating system more frequently than a long-term scheduler will. And what does that mean? It means that while a set of jobs are executing, they're changing states, that the operating system will wake up, by using an interrupt, resume itself, do some bookkeeping, select the process to run, and then get out of the way. So in an interactive system like your Windows machine, the operating system is firing all the time, very quickly, to make sure that each of the processes get a very small time slice to maintain the interactivity of the system. On a long-term scheduler, the operating system may not chime in at all until the current process is completed, because there's no need. That it will just start the process running and then run it, done. The operating system says, oh, this process terminated, now I'll select the next one to run. So you can, in those two types of systems, the short-term scheduler will consume more of the absolute time that we're measuring than the long-term scheduler will, because it's constantly waking up and performing operating system functions. So those are the two types. There's also the idea of a medium-term scheduler, which we'll get to on the next slide, but that's one that you might find closer on a Linux or Windows system. So when we talk about the performance of a process, we can say that it's I/O bound, meaning that it performs more I/O operations and it's sitting in that waiting state more often than it's executing. The inverse of that is that a process is CPU bound, meaning that it's performing lots of operations much faster all the time. So when you can think about, well, what is I/O bound and CPU bound? How does that relate to my processing, my jobs that I'm executing? An I/O bound process will get little to no benefit by having more CPU time. So if you want to improve the performance of an I/O bound process, you would improve the performance of the I/O device. So let's say that your I/O bound process is that you're writing a bunch of information to disk. You could improve the performance of that process by getting a faster SSD or even moving to an NVMe or a PCIe drive. that would improve the process there. If you went from a 2 gigahertz to a 5 gigahertz processor for that IO-bound process, there would be no benefit. Conversely, for a CPU-bound process, if you go from 2 gigahertz to 5 gigahertz, then the performance of that process will increase, meaning it will take less time. So that's how we might categorize the performance of a process. And in a long-term scheduler, those IO-bound processes we wouldn't want to wait for those to complete, because they're just going to be sitting there waiting for hard drives to come back with their operation complete. So it'd be useful to swap in, to run a different process that was CPU bound in those gaps. So a long-term scheduler, to reduce the total amount of time that it takes to execute all of the jobs, might want to interleave those IO bound and CPU bound processes to maximize the CPU usage and the IO device usage. That way, reducing the total amount of time that it takes to complete all the jobs in the long-term scheduler queue. A mix between the two is the idea of a medium-term scheduler. And this is the idea that that a process might there might be too many processes that are ready and we can't keep them in memory. So what happens is that the process is moved to disk and then moved back into main memory when it's selected. So this operation is clearly going to take much more time than just changing the state of the process and putting it on a different queue. So the idea here is that a process comes into the ready queue, it begins executing, it sits on the IO queue when it has information that it's waiting to get back, and then goes back to the ready queue. However, if for some reason, after executing, it's determined that this is a low priority task, a low priority process that can be moved to disk, it might move some of the memory space or all of the memory space of that process to disk. However, the process control block must still be tracked by the operating system, so that will stay in main memory. This note here is how a time-sharing operating system for a constrained environment might be structured. So the example they use is that in iOS, when you would run an app, everything else was suspended. They were moved from running state in IO state all the way back to ready, and only one process was ready to run. This has changed. Now there are multiple running tasks that are time shared on iOS as well as Android. Android is the one I'm more familiar with, but the idea here is not a full description of the concept, but how it might be implemented. So in the example where only one process is allowed to run, that means when we're not really time sharing anymore. That I have the active process that's running on the CPU, and no other process is allowed to run on the CPU until that process is complete. In modern versions of iOS and Android, that running process will still be going and will be playing Candy Crush, whatever it is, but there is potential for other applications to be scheduled to run on the processor while that foreground application is running. Those applications are limited in what they can do. They can no longer access the screen, and Android enforces this by calling these things services. And a service doesn't have a user interface. It sits in the background, and it is allowed to be time shared with the other foreground process, but it's restricted in how much memory it can take and how much processing time it can take. So one of the big cost of a time-sharing system, and even in a long-term scheduler and a batch system, is a context switch. And context switches are expensive. They take on the order of milliseconds for some processors, and that's a very long time for a modern processor. So a context switch refers to all of the operations that take place when a process goes from running to another I/O wait or just waiting, whatever the next state will be. All of the process control block information must be saved to memory somewhere in the operating system's control. And this takes time because it needs to move information, say, from a processor to, say, from process registers to main memory, take the program counter, etc., and store that information. Then the next job that is active is selected, and that state is moved in. So we switched context. In our previous example where we went from process P0 to process P1, that was one context switch when we interrupted P0 and resumed P1. And that not only costs the time of saving the information from process control block, but the amount of time that it takes the operating system to do any other accounting, such as, okay, reordering where those control blocks live in the proper queues, checking my interrupts, checking timers, anything else that needs to take place. That context switch cost is included in that time. So from the perspective of a process doing some work, that context switch time is just overhead. It contributes nothing to the running application. So there are ways to reduce context switch costs, but the cost is very high, and we wouldn't want to do this if we didn't have to. So those are, this is the big cost that's associated with context switching. And in modern processors that are trying to be secure, cache memory will also be flushed. So there are additional costs that might be associated with context switches. So there are two critical operations that the operating system must provide, and that's creating a process and terminating a process. So process creation will be dictated by the system in place. The example that we use here is Linux, that a process is created by what we call a parent. So that one process while it's running will request that another process is created. The process that requested a new process be created is called the parent, and the new process is called the child. This relationship creates a hierarchy of processes, parents and children. That's a tree with a single root. And then processes, after they are created, have some kind of identifier, typically a number, which we call the PID, the process ID. When a parent creates a child, there are options for sharing the resources of the parent. The parent and child could share all of their resources. The child could share a subset of their resources, or they could be excluded. Parent and children may share no resources. Execution of a child may, there are two options there as well, that when a parent requests the execution of a child, that they execute concurrently, or the parent waits until the child terminates. Typically, operating systems allow you to choose between all the resource sharing options and the execution options. So those are services that the operating system provides to process creation. On Linux, the first process is referred to as init. And that always has a PID of 1. In the example here, init has spawned login, kthread-d, and sshd. So we have our SSH server, kernel helper threads. This is a management daemon to take care of kernel helping, and then login handles terminal authentication. So when you begin logging into a Linux system at the terminal, the login prompt you see is controlled by a program called login, and when you successfully authenticate, it requests that a child bash is executed with your user ID and your group ID, and then from there you request processes within your bash shell that can then further create more processes. So that is how you can look at this tree for your user login. Excuse me. If you logged in via SSH, SSHD listened for your incoming connection and spawned a response to your authentication, so that when you accepted the TCP connection, that SSH created a new process to handle that particular that TCP connection, and then spawned your shell to log you in. And from there, you can request more processes be created by the same operating system call as the parent process used to create your TSH shell or your bash shell. So I've used the term address space, and now you actually have an idea of what that means. So the address space was that slide back on 3.6, I think is the number, where we had our text, our data, our memory allocations in the heap and the stack. So that's the address space of a process. And when you create a child, at the moment of creation, the child has a duplicate of the parent's address space. This is on Linux. And the child could continue executing at that point, or it could load a new program into it, a new source into it. This has gone over a little too quickly in this slide. The next slide's a little clearer on the process, but the idea is that when a parent forks a child, they are identical at that moment, except for one piece of information, and that is the return value of the fork call. So fork says fork a new process. The child process could choose to exec, and that would replace the current executing code. That would replace the text section. So our state diagram says, okay, so this is a different version of a state transition. Before it's referred to one process, now we have two. That we are in the parent process and we fork. Our execution continues along the upper path for that parent process. But after forking, there is also a new child process which starts execution right after the return of fork. And in this case, it will exec to start a new program in its place to become its process, and then it will exit. The parent has been sitting waiting for that child to complete execution, upon which it will resume. So let's take a look at the slide. This is a little easier. So here's the point that we care about. We have a program. It could be running for some time, doesn't matter how long, and then it forks. Fork is that call. It's eventually a system call to create a new process. And if the value is not 0, that could mean that it's an error if it's less than 0, or if it's a positive value, then that tells the parent the PID of the child. All right. If this call returns 0, that means we're in the process of the child. So after fork returns, the parent process will continue executing, and if it finds that the PID is positive, that means the fork call succeeded. We will then the parent then waits for the child to complete its actions. In this case, it's to the child begins execution at the same line. Says, is the PID less than 0? Well, it's not, because it's 0. It's in the child, so that's fine. But then if the PID is 0, the child says, oh, okay, replace me with this other program, ls. And so what happens in this example is there are two processes. The parent forks and requests that the ls program be loaded into memory of the child by the child itself. And then when that operation completes, because the child returns 0, it's the same code, then this wait call will return in the parent, and the child is complete. The Windows API, same basic idea. However, the calls are very different. But the idea is that it's a parent spawns a child. If the child creation succeeds, then we wait for the child to complete in the parent. I'll let you guys go through the Windows API for this if you wish. It's a little bit more complex, but the conceptual pieces are the same. So process termination is the other service that the operating system must provide for us. And there are two basic ways that a process can terminate, and that is to exit by itself. So the child is executing, issues the exit command, the exit system call with a parameter giving a return value, and that return value indicates success or failure to the operating system. A parent may wait for its children to execute, or it may not. The behavior there is operating system dependent. But and that's the normal way, the expected way that a child might terminate is that it finishes its operations and issues exit. A process may also be terminated, and the operating system may decide that a process needs to be terminated because it's consuming too many resources, or other reasons from the operating system, who knows what they might be, but that can depend on the current context of the system. It may simply be a timer. Or the parent no longer needs the child, so it decides to terminate it. So a parent can choose to abort a child, and it would identify it with its process ID of the child. In some operating, sorry, this is not going to work with the microphone. In some operating systems, a parent is not allowed to terminate before a child, and others they are allowed. So in an operating system that does not permit parents to exit without their children exiting, then that termination by the parent of itself will cascade to its children. And that would also apply if one process is terminated by one of its parents. So that's what that wait call is. It says wait on a process to exit, indicating success or failure. There are two interesting situations for a parent waiting on a process. If a child process exits but is not waited upon, meaning that the parent hasn't checked the status of that child's exit, that's called a zombie. But a parent that exits without waiting on a child, that process that was not waited upon, that child process, is called an orphan. On Linux, this is an acceptable state for a process. A parent may exit before a child. That orphan will become parented by init, the root process. So when we're going to move into the next section of our lecture here, which is IPC and why we might need it. One of the examples that you can think of is Chrome, and I believe everything except for Firefox uses the same rendering engine. So it's the same idea that a single process of a web browser might be more efficient for displaying multiple web pages, but if there's a problem with a particular website and that it's slow or its JavaScript is bad, causing the browser to crash because the browser is not written well, or the JavaScript is just confusing and it consumes all its resources, browsers will now use each tab as its own process and communicate information between them. So that's where we're going to go, is into IPC. But now is a really good time to take a break, and so I suggest just pausing the video for a few minutes, come back to it, and while you're taking that break, try to remember what are the components of a process, what's the difference between short-term, mid-term, and long-term scheduling, and then when you fork a child process, what does it share with its parent, and how that might occur. So inter-process communication is, in concept, just passing messages, passing information between processes. And we say that a process that is not interacting with other processes is independent. Otherwise, if it's passing information, working with another process to share data that it's cooperating. So a cooperating process is vulnerable to interactions of another process, but it's also dependent upon them. So why we would want to cooperate between processes is that we're sharing information between two processes. We want to work on them together, separate processes doing a portion of the work, or just simply to be modular. You can imagine in the web browser example that there's going to be a lot of modularity in having each tab be its own process, so it's easier to code, easier to maintain. And also it's also just easier sometimes to write a new process rather than to try to separate information between components of your application. So to facilitate passing information, we have communication that we refer to as inter-process communication, or IPC. There are two models that we will discuss: shared memory and message passing. In shared memory, let's take a look at the right. This is the simpler of the two, that there's just a block of memory, and this is taking a look at all of memory on the system, all RAM, and to this shared memory, process A and process B can read and write information, no problem. Message passing, there is somewhere in memory, there is a message queue, and there are a set of messages that go into the queue that are either placed there by process A or process B, and process A or process B can consume information out of that queue. So there are fewer restrictions around shared memory from a top-level perspective, that it's just shared, write to it, read from it whenever you want. A message queue will have a strict definition of how information goes into and comes out of the queue. This information got duplicated, I apologize. So to illustrate the differences between the two types of IPC that we'll discuss, we're going to use the classic producer and consumer problem. And the example that I'll try to use consistent language for, is that Spacely Sprockets produces sprockets, and then uRentamade buys those sprockets to make more rosies. And if the producer can create an unlimited number of sprockets to be consumed, then that's an unbound buffer. An unbounded buffer version of the problem. If Spacely can only produce a certain amount of sprockets before at least one must be consumed, that's the bounded buffer problem. So this is where we start, our shared information. And we haven't, in this shared data section, we haven't described how we share it, just that we're sharing it. So the pieces that we're sharing are this buffer, which has 10 elements in it of type item, and a counter for the number of in and the number that are out. So from the producer's perspective, it is going to try to produce as many sprockets for an infinite amount of time, one after another, sprocket, sprocket, sprocket. The first thing that the producer checks is there space? So here, these two lines, this is an infinite loop. It's just spinning, checking if it adds one more item to the buffer, will that equal the end of the buffer? So the beginning of the set of produced sprockets to the end of the set of sprockets. If those are the same, there's no more capacity in the buffer, so it can't do anything. But it keeps checking until this condition is no longer true. When there is space in the buffer, then it will produce the next item and increment the next available item. So if we just produced one item, in would increment to 1, and there would be an item in position 0. Looking at the consumer, if in is equal to out, that means there's nothing in there, so we can't do anything. So then it would wait until that condition was not true. So in the case of one item, in would be 1, out would be 0. So it would consume that one out the one item at the out index and then increment it. So when in is the beginning of our buffer and out is catching up to it. So sorry, in is the end of our buffer, that if we were to keep adding items, we might add 3 at a time, and when we came into this loop, then in would be 3, out would be 0, and out would need to catch up by continually consuming. So that was a bit fast. Spend some time with this concept and just understand that between the producer and the consumer, that buffer in and out are shared between them. We haven't discussed how, but just assume for these two code segments that in and out are shared between the consumer and the producer processes. So shared memory is under the control of the the processes participating. There are some race conditions in, if those of you that understand race conditions and study them elsewhere, you'll notice there's already a race condition in those previous examples of when the information is taken from the buffer by one process and when in and out are incremented. So with two processes, I believe that the race condition, there is still a race condition, but regardless, you can look at the race condition on your own and see that it's still there. So to avoid race conditions, synchronization addresses those, and the reason that I'm not going into it now is because we'll talk about it in chapter 5. The concept here to make sure that you distill from it is that shared memory is under the control of the users, not the operating system. So the users here are the processes. So the processes control access to shared memory, access to information within shared memory. The operating system does not. Message passing is an alternative method to sharing memory, and the idea is that I'm going to send a message as similar to sending something in the mail. So using our Spacely Sprockets example, that Spacely would send a sprocket to uRentomade, and uRentomade would receive the sprocket. That's the whole concept, the whole big concept. The message itself could be of a fixed or a variable size, but the operating system provides that service for sending and receiving messages. There are additional models of passing messages. So there needs to be some way of sending and receiving messages. We'll call that a link. Then once we have a link between process P and Q, they can send and receive information. Based on the operating system, links may be established in multiple ways. We don't necessarily have to describe the mechanism for establishing a link, just that there might be multiple ones. But we might want links that can have just two processes, or they might have multiple processes where you might have multiple senders, multiple receivers, or one receiver, multiple senders, or the other way around. Then the other concept is whether or not that link is bidirectional, meaning if two processes establish a link, can they send and receive, or can they only send, or can they only receive? So unidirectional means that if P and Q establish a communication link, P can only send to Q and Q can only receive from P. In a bidirectional link, P could send and receive from Q and Q could send and receive from P. And then there is the cross product of, are there multiple processes participating? Does everybody need to be connected? That can be in the parameters for establishing links. So the message passing is a logical construct that has a set of constraints. So direct message passing would say that P sends a message directly to Q, or if it was indirect, P might send a message to somebody, and direct receipt would say that Q receives a message from P, or indirect says Q receives a message from anybody or some set of processes. There might be synchronous or asynchronous message passing, meaning that P, upon sending a message to Q, must wait for Q to receive the message. That's a synchronous message passing, or it might be asynchronous, that P sends the message to Q and then goes on. It's not forced to wait. And there might be, the operating system may provide some kind of buffering, or it might require that the processes buffer themselves, meaning if there's not space, if there's not capacity upon the link, that the process itself would handle that. So those are the logical components, the service that we want to provide for this concept of message passing. Implementing a message passing mechanism, that's different. That will depend on the underlying hardware and the design choices of the operating system, whether or not it uses the network card, some kind of hardware bus, or even shared memory to pass messages. So again, that direct communication, here the function signature of the system call is enough to tell us what that means. That P sends a message, in this case, Q sends a message, so send to P this message, and that P would receive from Q by explicitly declaring who it would come from. And this doesn't say that the link is one way, but this does establish a link because it's explicit who the endpoints of the link are. Indirect communication is a little different. We can think of this as a mailbox, like a post office box. The mailbox has a unique ID, and processes can communicate with that mailbox if they are granted access to it. Access to the mailbox is a different issue, but just assume that only a certain number of processes are interested in that mailbox. Then a link between two processes goes through the mailbox, so that one process would place a message in the mailbox and another would come by and take that message from the mailbox. In this way, there can be multiple links between processes, but that's through the mailbox itself. And this mailbox may be unidirectional or bidirectional, meaning that only a select set of processes may place items in the mailbox and only a select set of processes may remove the mailbox. There's one more concept here that's not enumerated, and that is that a mailbox may be owned by the process itself, or it may be owned by the operating system, or it may not have an owner at all. It may just have permissions. So who owns it refers to who has the memory typically, but who's in control of it. So for an operating system that provides indirect communication, they will need to create a new mailbox, send and pass messages through the mailbox, and then destroy the mailbox. And here our send and receive are two mailboxes, to send to a mailbox and receive from a mailbox rather than a process. In this world of indirect communication with multiple senders and possible multiple receivers, when a message is placed in the mailbox, who receives the message is a question. So how do you solve this question? One might be to assign priorities or assign some kind of selection mechanism, just like scheduling a process on a processor. There might be some kind of selection mechanism between processes based on priority. Other solutions would be to allow that link to be between at most two processes. Well, now that feels like direct communication. And the other is that it might be the first one that executes that gets to get it, or again, let the operating system delegate which process will receive it. Message passing, when this is the asynchronous versus synchronous communication. So a blocking send or a blocking receive is synchronous, meaning that send message, sending a message, if that is synchronous, this function call will not return until it has been received by another process. So blocking send, the sender does not continue processing until it's been received. A blocking receive does not return until the information has been moved into the process that's asking for it. Non-blocking is the opposite, that when a process sends a message, places it in the mailbox, in the queue, that it just continues operating. A non-blocking receive, in terms of the function call, it will either get a message or it will get no message saying there's nothing there. The special case where both the sender and the receiver are blocking is called a rendezvous protocol in our book here. So in a synchronized producer-consumer, the producer-consumer problem with the message passing system is very simple. Keep producing items, so when one is trying to be sent to the next consumer, it is just waiting to be consumed, and this call will not return until the consumer returns from receive. So taking a look at their execution independently, starting up the producer process, this loop will begin execution, and then this send call will, when it's invoked, will just block. The process goes into the waiting state. From the consumer's perspective, when it starts up, it will go into this infinite loop, call receive, and it will stay there until an item is available to be received. It doesn't matter which one starts first. These calls, the receive call will block if the producer has not sent until it sends something. Once it is sent, then the receive call will return in the consumer thread. In the producer thread, the send call will then succeed because it has been received. In that producer and consumer example we just saw, there's no buffering because only one item can be outstanding at a time. But otherwise, you might want to allow a mailbox or a message to be queued, meaning there are multiple that are waiting on the link between two processes. That's what we just saw in the previous example, that there's 0, that's a rendezvous. Bounded capacity, meaning that it can hold as many as n messages or n bytes. An unbounded capacity is that the sender never waits. It always just sends everything, and it doesn't really care. So shared memory on a POSIX system is created by SHM open with a set of parameters. I'll let you take a look at those. And then we set the size, in this case, to 4 megs. And then we can write to our shared memory. This should be SHM-FD that is writing to that memory just by placing bytes in that location in memory. So taking a look at the slide for it, we set up our parameters, our size, our message, and then our file pointer. And our producer opens the shared memory, sets the size of it, and writes to it. The consumer will open up that shared memory. In this case, it's got a name. The identity of it, the shared memory segment is identified by the string, reads from it, and that's it. When it's done with it, it unlinks it as so that it is no longer part of destruction of the consumer. And the other thing to notice here is that the open call created it here in the producer, and we did not create it in the open call for the consumer because they're just reading from it. So here, this is by practice in shared memory, this is a one-way link, unidirectional link. Mach is message-based for IPC, and there are just 3 system calls to send, receive, or ask for a remote procedure call. Mailboxes are created by port allocate, and there are other options on placing messages in a full mailbox. That the sender could wait until there's space available, wait for a amount of time, return, or cache its message. On Windows, it's ALPC, which we don't have direct access to. That's handled for us by the operating system. And the mailboxes have their identifier, which are themselves ports. And this is a little bit more complex of a system. There are three components. There's the idea of requesting that communication occur. Then there are client and server ports. And then there's a small shared section for a quick transfer of information. So the diagram is easier to understand. The client will issue a request on the server connection port, not the communication port, to make a new communication link. Once that link is established, the server returns a handle to the client that gets it to the server side of the communication link, and it already has the client communication link in the connection port request, and this is where messages are passed. If there are shared memory, basically essentially the same idea of shared memory, that shared objects can be used in this shared section object. So it's the Windows version, it's a little bit more complex, but the idea is that we're passing information first by establishing a connection, and then we have a communication link along with a little ancillary area to send information to just inspect it like shared memory. There are other concepts. There's the idea of a socket, RPC, remote procedure calls, pipes, and RMI is very similar to RPC, but with a little bit more structure. So sockets are a generalized form of unstructured, by its nature, unstructured message passing. We typically think of sockets when they're related to networking protocols. You can use, there are other types of sockets that are not necessarily IP sockets. Here we have an IP socket as our example. So the socket is associated with an address and a port, in this case the 161.25.19.8, port 1625. The link is established between two ports on two hosts or the same host, and that is the endpoint connections, and messages are sent and received to those particular ports. So loopback, that is your local system. That 127.0.0.1 is always your local system. So a socket identifies the two endpoints of a link by its address and port. Here you have your host, which might be connecting to a web server on port 80. So we have the address of the server and its port. Those two portions make up the endpoint of the server. The endpoint of your client to send information back to is this 146.86.520, port 1625. There are more than 3 types of sockets, but the ones that we will deal with in networking are connection or connectionless. Connection-oriented sockets are TCP, connectionless are an example is UDP, and then multicast, I apologize. So in this example, we have a date server, which creates a new endpoint, and this server socket is 6013, so whatever the public address of this server, port 6013, and it will accept a client that makes a connection that will establish the link between the two, for which it can write information to the client through this print writer object, send the information, and then close the connection. There's quite a bit more that goes on there, but the idea here is that we're using a socket to connect, and the socket has an address and a port, which will very much look like a mailbox from the local operating system local operating system concepts. RPC doesn't pass messages as abstract data. It sends a more structured message which says, execute this command. And this mandates that the client and the server have an understanding of what the command is and how the arguments are formatted. So an ls command would have a directory, and executing the RPC call for ls would require that the directory that was being acted upon be provided to the server to run the command. Because different machines have different architectures, different ways of representing data, there needs to be a common form of any information that's passed between the two. So the directory, the name of the directory would need to be marshaled into that common form, and that's what it means to take the parameters for an RPC call or any network information. We are going to take the parameters, put them in a known format that the other side can understand. So we marshal the parameters to the call and issue them to the server. So the server then unpacks those parameters, unmarshals them, performs the procedure, and then optionally sends a result, marshaling it for the client to receive. This is the marshaling. The easiest motivation for it is to consider big endian and little endian. And in a big endian system, the first byte is the most significant, and the last byte is the least significant. In little endian, it's the other way around. So that is why we must marshal information, so that when we talk about the number 4, which would have, say, 2 bytes starting with 0000, 0004, if we flip that order, that would be a different piece of data on a different machine. So that's why we marshal information. When we issue an RPC call, there are different policies around executing that call. It could be execute this exactly once, meaning if you've got a command to say, launch the Batmobile out of the cave, you only want to do that once, or it could be at most once. So what's the difference? Well, at exactly once means that this has to take place. At most once means 0 or 1. So this command may or may not succeed. So to establish exactly once and acknowledge that the Batmobile has been launched is a more complicated protocol than at most once. So there is one more component to RPC, and that's the idea of what I will call a directory. And the way a directory works is that there is an RPC service that the client sends an RPC message to execute some command to a server, and the known matchmaker port on the server is the destination of the message. The server receives the message, says, okay, who can service this RPC call? So then it sends the directions to the client where to send its actual request. The client receives the new location to send that command, and off it goes to find that particular server that will be able to service the command it's interested in. So this matchmaking service is a directory of where a client can go to get its RPC services invoked. Pipes are another method of IPC, and they are local tubes to carry information between processes. And again, they have the same concerns. Is this pipe unidirectional or bidirectional? Can both processes write and read, or can only one read and only one write? If it is bidirectional, can reading and writing take place at the same time? Half duplex, sort of a strange way to say things, half duplex says only one operation can take place at that time, either reading from one end of the pipe or writing to that same end of the pipe. Full duplex says that you can read and write at the same time. Pipes and how they can be established, there might need to be policy around that, whether or not pipes can exist between any process, parent and children, and can the pipes be used over a network. There are 2 pipes that we talk about in the book. Ordinary pipes, those are the pipes that exist between the parent and the child. And named pipes are those that don't require a parent-child relationship, so that addresses the third point here, whether or not a parent and child relationship must exist. So an ordinary pipe, this is not what I think of an ordinary pipe, but the pipe that we will see on Linux systems is when you have a bar between one command and another, is that a producer writes to one end, that's the right end of the pipe, and the consumer reads from the other end. Ordinary pipes are unidirectional, and they require a parent and child relationship. On Windows, these are called anonymous pipes, and there's a code sample in the book. What we want to pay attention to here is that from these arrows are a little weird, that FD0 for the parent is the writing end of the pipe. And when the parent forks the child, these file descriptors are duplicated, because that's how this works. You know, that's what happens when you fork a process, is that the address space is duplicated. So the parent will write to file descriptor 0, while the child will take the read end of the pipe, which is file descriptor 1. And so the parent, upon forking the child after that succeeds, will close its read end, and the child will close its write end, so that information flows in that single direction. Take a look at the example, the code example in the book. It's pretty good for that. Named pipes are pipes that live elsewhere, that processes can connect to and establish a link between. And because they exist outside of the processes, there is no parent-child relationship required. And that way, processes can use a name pipe for communication. So those are our components of chapter 3. And that's week 4. So make sure that as you've gone through this lecture, the pieces that you make sure you can recall are the notions of a process, what a process is, a program in execution, the basic unit of computation in your system, the features of processing, with the scheduling process, termination, communication, context switching. Make sure that you have at least a general idea. Well, make sure you understand IPC and the 2 mechanisms that we described: shared memory, message passing, as well as sockets and the client-server model that we have in our information age of the internet. So with that, I thank you for your time, and I will see you in the next video and in the next Q&A session.